This conference will now be recorded.
Good morning. Today we are going to learn very interesting lessons from kinetic theory of gases. So today we'll learn what is called degrees of freedom and why is it necessary to learn. We'll see that. And an important law which is called law of equipartition of energy, that we'll learn. And at the same time we'll learn how to calculate specific heat of monoatomic, diatomic and triatomic gases or triatomic molecules. Okay, so let us first learn what is called degrees of freedom. So degrees of freedom, this word itself can say you something. Freedom means if I suppose if I have a particular molecule and I leave it free to move. So what are the degrees of freedom in the sense, like in which dimension it is moving and what all direction it is moving. So these are actually specified by saying degrees of freedom. If I say very accurately and scientifically what is degrees of freedom, it is the sorry. So it is the number of independent coordinates, number of independent coordinates required to specify the motion or configuration of a system. Okay, it is the number of independent, see you can see independent coordinates. It is the number of independent coordinates required to specify the motion of a system or the configuration of a system. It is actually called degrees of freedom, and mathematically it can be written as small f is equal to 3n minus L. This is the expression 3n minus L. Okay, I'll just stop here for okay, I'm just giving you this equation. Now I'll just give you some examples, then I'll come back to this equation again. What is n, what is L, etc. I'll discuss first. Let us say one molecule, okay, one molecule or atom is confined to move in a particular axis, suppose x axis. So its motion is actually constrained, or constant means it is bound to move in this x direction. So if a particular object, here since we are reading in kinetic theory of gases, I say gas molecule or gas, suppose an atom, it is confined or constrained to move in a single direction, then its motion is actually 1D motion, right? 1D, one dimensional motion. Okay, one dimensional motion. So how many coordinates do you require to specify the motion? In a 1D dimensional motion, and you have only one atom or molecule, so you require only one coordinate, right? One coordinate. So in this case, degrees of freedom will be 1. Okay. Suppose the same molecule is constrained to move in a plane, in a plane, then it is moving in two directions, right? In a plane means someone is moving in this direction and this direction also, right? That motion will be in the plane. So plane, in the plane, to specify the motion of an object in a plane, you need two coordinates. So this is 2D motion for a particular object. This is 2D motion. So you require two coordinates. Two coordinates. This is motion in a plane. This is motion in a particular line or direction. Motion in a line. Motion in a line, along a line. And this is motion in plane, in a plane. Okay, so two coordinates you require, two independent coordinates. Independent means you cannot express y in terms of x. You cannot express y in terms of x. There is no way to express y in terms of x. This is what I mean to say. So x and y, you need two independent coordinates. Here you need only one independent coordinate, right? Similarly, if I say that an object, suppose here a gas molecule or an atom is moving in a three dimension, in three dimension means it is moving in three different directions. Okay, suppose it is moving in three different directions, x, y, and z. So this is actually, this whatever I said as motion, this is actually, there are motion. I'll tell you, there are three types of motion. But what I am saying now, this is suppose translation motion. Translation means what? It changes its position in particular direction. So it can move along x-axis, along y-axis, along z-axis. So it has three translational, three independent coordinate you require: x, y, z, x, y, and z. Actually, this is called translational motion. Whatever motion I have discussed so far, this is translation motion or translational motion. What else you know about motion? Motion can be rotation also, right? Motion can be vibration. So there could be rotational motion, there could be vibrational motion. All these motions are possible. Okay. So in kinetic theory of gases, we are learning degrees of freedom. That means we say the number of independent coordinates required to specify the motion of a particular gas molecule or atom. Okay, so that is degrees of freedom. Now come to this part. Okay, let before I clean this, let me tell you few more things. So translation also can be three types, right? Sorry, translation I have told already. Rotation. Rotation can be in three different directions. See, rotation means what? Rotation can be about x-axis. Rotation can be about y-axis. Rotation can be about z-axis also. So there can be again three rotational degrees of freedom. So when you say motion, there are three types of motion. One is translation, translation. There is rotation, and the third type of motion is vibration. Vibration. Okay. Okay. So in kinetic theory of gas, if I take a single atom, this single atom has actually it is a point atom, right? Point. Each and every atom or molecules, like a single atom is actually considered as a point, so it doesn't have any direct dimension. So a point can only move, it does not have any rotational or rotational degrees of freedom. It has only translational degrees of freedom. But when you have diatomic molecule, you have two atoms. It is a kind of dumbbell shape, right? So this dumbbell can actually rotate about a, an axis which is perpendicular to this uh, line joining this atom, right? I hope you are agreeing with me. Okay. Or it can vibrate about the mean position of this line, isn't it? I hope you agree with me. Vibration means what? Sometime this molecule will go this way, this atom will go this way, and this way. Another atom also will move this way and this way. This is vibration. Okay. So about the mean position of this line of joining, they can vibrate. Okay. So this is actually called vibrational degrees of freedom. So there could be three types of degrees of freedom: rotational degrees of freedom, translational degrees of freedom, and vibrational degrees of freedom. But for all molecules, you cannot find all three degrees of freedom. Some cases, all three degrees of freedom will not be there. Some cases, only translational degrees of freedom will be there. Some cases, there will be rotational degrees of freedom and translational degrees of I hope now the sound is recovered, right? There was some problem. Okay, anyway, now I think, madam, are you able to hear me now? Okay, I hope. So, three N so yes, is the significance of this particular equation and how do we this? Okay, okay, so this is actually number of degrees of freedom F is equal to 3n minus L. So what? Okay, just leave this number. Just leave this number. You come to this. Okay, so this is actually when a particular object is moving in. Like this is 3 means this is in 3 dimensions. Like it is actually this number is denoting 3 dimension. 3 dimension. This is space. So we have to write this as 2 when it is two-dimensional motion. Okay. So for 2 dimension, we have to write 3 as 2. So in general, we are considering the motion in 3 dimension or motion in space. So motion in space has to be specified at least by 3 coordinates. Okay. So one for 1 dimension. Okay. Now what is this n? N is the number of atoms or particular object. Number of atoms in this case. Number of atoms. Suppose there are 2 atoms, then you have to write 2. If there are 3 atoms, you have to write 3. So this is what it is. And what is this? This is actually constant, number of constants. Number of constraint, number of constant equation it says. But you remember what is this? This is actually the limitations. How many limitations you have? How many limitations we have? Okay? How many limitations you have? Okay? Let us just use this formula and try to find out degrees of freedom for various systems. Let me tell you, f is equal to 3n minus l. Suppose I want to know degrees of freedom, degrees of freedom, degrees of freedom, degrees of freedom for one monoatomic gas, for a monoatomic gas. Okay, so monoatomic gas. So how to apply this for monoatomic gas? Suppose it is a motion in space. So F will be actually 3 into mono means 1 atom, okay, and minus L. In monoatomic gas, actually there is no constant, there is no limitations for moving. Monoatomic means single atoms you have, and it can move in all 3 directions. Okay, it can translate in all 3 directions, but it does not have any vibration. Okay, so or there is no limitations for its motion, so L is equal to 0. So you have 3 independent coordinates to required to specify the motion, of a monoatomic gas. Okay, so three independent coordinates, and all three are actually translational translation degrees of freedom. Translational degrees of freedom. Okay, translational degrees of freedom. All three are translational degrees of freedom, because if monoatomic gas, it it does not have any rotational, so no rotational degrees of freedom. Degrees of freedom sometimes can be written DOF, and it does not have any vibrational degrees of freedom. Vibrational degrees of freedom. Okay, all right. So these are the things. Okay, now if we want to calculate the degrees of freedom for a diatomic gas, so this is, so you can see for a monatomic gas degrees of freedom is 3 when the motion of the gas in space. Now we'll see for a diatomic gas how many degrees of freedoms are there. Okay, you might be thinking, sir, what you are teaching, this is stuff of classical mechanics, but you are just teaching it here. Yes, these are the stuffs of classical mechanics, but we are teaching because we want to calculate the specific heat. We want to know the energy of a particular uh, gas, okay, at particular temperature, okay, at equilibrium. So what is the total energy of a particular gas? So that we want to know. So here, if I say degrees of freedom for a diatomic gas, so then for a diatomic gas, so let me just draw the configuration of a diatomic gas. So this is a diatomic gas. So how many atoms are there in this case? So there are two atoms. So I'll write n is equal to 2. So how many constant equation is there? Actually, it has two constant equation. Sorry, one constant equation. See, they are actually they cannot move along this direction. Okay, because they are just confined. They will be always at. This is kind of a rigid. Uh, in the sense it is having a rigid. Suppose a stick. Stick is actually if you just have a dumbbell, you can understand that if you know the dumbbell. So these two cannot move. If this is a rigid one, these two cannot move in this direction. So it has L is equal to one constant. So if we want to find degrees of freedom, then 3 into 2 minus 1. So you'll get 5 degrees of freedom. So it has 5 degrees of freedom. So this motion is not allowed. So there are actually three. There are three. Sorry, you can have if this is actually treated as rigid rotator. Rigid rotator. Okay, rigid rotator. So you have three translation like this. This can move in this direction. Okay, along any like any. It can have three translational motion. Okay, and it can have two rotation. It cannot have any vibrational motion because if it is a rigid one, it cannot have vibration along this way and this way. Okay, it does not have a vibrational degrees of freedom. It has three. So 5 means three translation, translation, and two rotation. I'll tell you how it is two rotation. Okay, two rotational degrees of freedom. Rotational means since it is okay. Let me write is here. It is 5. So three translation and two rotation. Okay. So how it is rotation? See, if any perpendicular line you draw, so one will be in plane. It can rotate in plane or perpendicular to its plane. Okay. It can rotate about an axis which is perpendicular to its plane, right? And it can rotate like this also. Okay. I hope I am able to make you understand. It can rotate in this direction like this vertical circle or a horizontal circle. Okay, that is what I want to mean. So there are two rotational degrees of freedom. So there are two perpendicular axes for this dumbbell shaped diatomic molecule, which is actually acting as a rigid rotator. Okay, so there is no vibrational motion in this way. Okay, so it has 5 degrees of freedom. Similarly, if you have a triatomic molecule, for triatomic molecule there could be three cases. Okay, let me tell you. Let me write degrees of freedom of a triatomic molecule. Triatomic molecule. Triatomic molecule. There could be two situations at least. So see, in triatomic molecules, if the molecule is linear molecule, okay, it can be a linear molecule or it can be having a triangular shape. Sorry, it can have a triangular shape. Triatomic molecule can have a shape like this, like NH3, etc. NH3, I think this is the configuration. Okay, and H2O, or I think CO2. I hope CO2 is actually this linear chain, linear molecule, and this can be H2O, etc. So there are three atoms, okay? H2 and this O, or NH3 is another good example. So you look here, here you have three atoms and two different configuration. One is linear configuration, another one is triangular configuration. So how do we calculate degrees of freedom in this case? We know F is equal to 3n minus L. Okay. So here, anyway, there are three atoms. So I can write in each case n is equal to 3. But what about L? See, there are two constraints for this configuration. Okay. For first case, there are two constraints. Okay, two constraints. And for second case, n is equal to 3, we know, and L is equal to 3 constant. That means this distance cannot be altering. This distance will be always fixed because it is a rigid molecule. So if it is 5 centimeter, it should be always 5 centimeter, kind of that. Okay, so this is a constant equation. So constant, so there are three constants. For three constant means there are three number, L is equal to 3. Now if we write degrees of freedom for this, so 3 into 3 minus L is 2. So you have 339, so 7 degrees of freedom. Okay, 7 degrees of freedom. And for this triatomic molecule, you have 3 into 3 minus 3. So you have 6 degrees of freedom. Okay, so in this case, actually uh, there will be 3 translational already. There will be 2 rotational and 2 vibration. 2 vibration means it can vibrate in this direction. Okay, so there are 2 vibrational degrees of freedom also here. Okay, and in this case 3 translational and 3 vibration, there will be no rotation. Actually there will be no rotation. There will be 3 vibration along this, along this, along this, and there will be no rotation. 3 translation, 3 rotation, sorry, 3 vibration. Okay, anyway, so you can know, if you are not understanding how, why 3 rotation, why 2 vibration, no rotation. Okay, if you are having these doubts, this will be cleared again when I discuss uh, numerical problems later. Okay, so this is about degrees of freedom. Now why do we need degrees of freedom? We need degrees of freedom to know the total energy associated with a particular gas. Kinetic theory, when I am saying kinetic theory, then generally we want to write total energy. And what type of energy? It is the motional energy, not the potential energy. Okay, potential energy for ideal gas, at least in the kinetic theory, we have just excluded the interaction between the gas molecules or gas atoms. So there will be no potential energy, only the kinetic energy. So there are three types of kinetic energy. One is K translation plus K rotation plus K vibration, kinetic energy plus kinetic energy vibration. Okay, let me write this as K. So total kinetic energy of a particular gas. So at particular temperature, at a particular equilibrium temperature, some absolute temperature, what is the total kinetic energy of particular gas? So suppose a diatomic gas, or a triatomic gas, or a Monatomic gas, what is what is the total kinetic energy? So that is what we need to know. So how to know? If I know the degrees of freedom, how would that help me to find out the total kinetic energy of a gas? See, for that you need to know that the degrees of freedom actually is the basis. Degrees of freedom is the basis of is the basis of law of equipartition of energy. Law of equipartition of energy. So degrees of freedom is the basis of law of equipartition of energy. Now we'll learn what is law of equipartition of energy. So according to this law of equipartition of energy, for any dynamical system in thermal equilibrium, the total energy of that particular system is shared equally by all degrees of freedom. Okay, if you have the total kinetic energy, so that total kinetic energy will be shared by all degrees of freedom. That means if you have 3 degrees of freedom, then it will be equally distributed in 3 degrees of freedom. Okay, so this is the statement of law of equipartition of energy. So law of equipartition of energy states that for a dynamical system in thermal equilibrium, the total energy of the system is shared equally by all degrees of freedom, and the energy associated with each degrees of freedom, if its degree of freedom per molecule okay, each degree of freedom per molecule is half kBT, where kb is the Boltzmann constant and T is the absolute temperature at equilibrium. I'll restate this statement. So law of equipartition of energy states that for a dynamical system in thermal equilibrium, the total energy of the system is shared equally by all degrees of freedom, and each degree of freedom is associated with associated with an energy. That energy is given as half kBT. So the energy associated with each degree of freedom per molecule is half kBT, where kb is the Boltzmann constant. Now we'll write what is uh, let me write this in mathematically. What is mean is this? You look. This is for an example. Uh, for a monatomic molecule, we have seen the degrees of freedom is monatomic molecule or monatomic. Okay, so 3 1 minus 0, so 3 degrees of freedoms are there. So there are 3 degrees of freedom, so each degree of freedom is sharing an energy of half kBT. each degrees of freedom each degree of freedom per molecule, this is half kBT. So there are 3 degree of freedom, so 3 into half. So what is the total kinetic energy? Total kinetic energy will be 3 by 2 kBT. Each degree of freedom is carrying 1 by 2 kBT or half kBT. So 3, there are 3 degrees of freedom, so there will be 3 by 2 kBT per molecule. So this is the total energy of a monoatomic gas, or mean kinetic energy of a molecule of so this is, I think you should write it is gas. So monoatomic gas, according to kinetic theory of gases, the mean actually this energy actually is meaning mean kinetic energy. Mean kinetic energy. Okay, mean kinetic energy, all these are actually mean kinetic energy. So kinetic energy half m v square. See, there are translational kinetic energy kt. So kt is half m and summation over vi square. I can go 1 to 3. That means 1 is actually, see, it can be vx, it can be vy, it can be vz. So 3 directions. Okay, in 3 directions the motion or the velocity can be there. So kt is half m vx square plus half m vy square plus half m vz square. So if you take the average, so that average for each direction, the average will be half kBt per molecule, half kBt. And the kinetic energy what we get in this way is also called mean kinetic energy of that particular gas. Okay, similarly, if we write for diatomic gas, what is the total kinetic energy? Diatomic gas. So what is the number of degrees of freedom in this case? 3 into 2 minus 1. So it will be 5. Okay, for a diatomic gas, 5 by 2 kBt, because each degree of freedom per molecule carry or share half kBt energy. Okay, so 5 by 2 kBt. For diatomic molecule, there can be 7 by 2 kBt. For for a linear one, linear, and there will be 3 cavity for a triangular molecule. For a triangular molecule, triangular molecule. Okay, for a triangular molecule. Sorry, molecule. All right. So this is actually law of equipartition of energy, and to find out the mean kinetic energy of a particular gas, we need to know law of equipartition of energy, and degree of freedom is the basis of law of equipartition of energy. So that's why degree of freedom is important, and we have learned that. Now, before I go to find out the specific heat, let me tell you there are few significance of this law of equipartition of energy. We have learned already what is the importance of this particular law. Still, we will just point out those. So first is that ideal gas provides an important application of equipartition of energy that we have seen. With the help of equipartition theorem, we would be able to derive the formula of ideal gas as well as internal energy. Internal energy we have already found out, that is the mean kinetic energy. It can be useful to understand the Brownian motion easily, that we will see sometime in this chapter. This law can also be used as astrophysical tool. Using this law along with the virial theorem, we can easily estimate the average of distant star, that is the astrophysical application, and it is also used to study current condition of star formation. Anyway, so you can just remember these points. Now, even though there are many usefulness of this particular law, but there are few flaws also. Let us see what are the flaws or limitations. The law of equipartition holds only for ergodic system, that means infinitely slow system, that at each step of the system, evolution of the system will be in equilibrium, thermal equilibrium. Okay, which implies that the law of equipartition of energy fails when quantum effects are introduced. Okay, because it is actually very instantaneous phenomena that occurs in quantum case. So among three energy distributions, quantum effect dominate vibrational energy of atoms or molecules at high temperature. High temperature only there will be vibration above 1000 Kelvin. But this limit is overcome by newly introduced thermodynamical systems. Okay, so these are few limitations. So at very high temperature, you have only vibrational degrees of freedom. Now we'll learn heat capacity, and we'll try to find out the ratio, CP/Cv ratio. Okay, specific heat capacity. So specific heat capacity, we know that if you know the total energy E, then dE by dt will give you the specific heat at constant volume. Actually, if you, okay, let me write this as U. If you know the total internal energy or mean kinetic energy, then you can write this as Cv. Okay, du is equal to Cv into dt, or du dt is equal to Cv. So you can find out the molar specific heat at constant volume. Okay, that we can do. So we can write this particular term, internal energy, from equipartition, law of equipartition of energy. Let us find out specific heat capacity for a monatomic gas first. For a monoatomic gas. So when I say specific heat capacity, then there are two actually at constant pressure, that is Cp, and another one is Cv. And we can find out the ratio of Cp by Cv also. Okay, all right. Let us say for a monatomic gas. So what is the degrees of freedom? Degrees of freedom is 3. So what is the mean kinetic energy or the internal energy? That is 3 by 2 kBt per molecule. But you are, so this is, let us say this is U is equal to U, small u. That means this is per molecule. This is per molecule. So per molecule. So the total kinetic energy will be 3 by 2 n means Avogadro number, Na suppose, and kBt. This is actually uh, for a mole, for a mole, for a mole of gas. So this is the internal energy or average kinetic energy for a mole of gas at thermal equilibrium. So now this is for a monoatomic gas, obviously we are doing. So if we write Cv, so molar specific heat, that's why I'm just calculating this particular term for a mole, because I'm going to write specific heat for a mole, or the molar specific heat. So du dt means 3 by 2 n a kb, Na into kb, Na kb. So Na kb is written as R, the universal gas constant R, where Na, Avogadro number, into kb. This we have already discussed. So Cp, sorry, Cv we have got. We have to find out Cp. We know Cp minus Cv is equal to R again. So what we can write as Cp? Cp we can write Cv plus R. So what is Cv? Already we know Cv is equal to 3 by 2 R, and this is another R. So it will be 5 by 2 R. That means you get 2.5 R. Okay. Now from here, since we have got Cp and Cv, we can write down one more thing from here. So for a monatomic gas, we have got Cp is equal to 5 by 2 R, and Cv is equal to 3 by 2. This is R. Cv 3 by 2 R. If we take the ratio, then we'll get gamma. Gamma is Cp by Cv. So 5 by 2 divided by 2 by 3. So you get 5 by 3. So this is gamma is equal to 5 by 3. Okay, so if you just 1 1.6 1.67 something like this, okay, this will be the gamma. okay, for a monatomic gas. All right, we'll just go further. So we'll go for specific heat. I'm writing SP for specific heat capacity for a diatomic gas molecule. Okay, for a diatomic gas, as you know, the degrees of freedom is actually 5. Okay, we have already discussed. You can just go back and see in the video. So degrees of freedom is 5. So you get if I write for a mole, U will be 5 by 2 in a kV, right? So that means 5 by 2 R. Okay, this is U. Sorry, this is obviously T will be there. So CV will be du by dt. That means 5 by 2 R. Okay, CV is equal to 5 by 2 R, and then CP will be CV plus R in the similar way. So you'll get 5 by 2 R. Okay, now you have got molar specific heats at constant pressure and constant volume both. Now you can find out the gamma for diatomic gas. Cp by Cv is equal to 7 by 2 R divided by 5 by 2 R, so it will be 7 by 5. Okay, so 7 by 5, if we just do that, so we get, so nearly 1.4. Okay, 1.4, not nearly, it is exactly, it is 1.4 for diatomic gas. Similarly, for triatomic gas, there are, for diatomic gas specific heat, molar specific heat capacity, see, there are 2 degrees of freedom. One is 5 degrees, 7 degrees of freedom, and another one is 6 degrees of freedom. So it can have actually 2 different sets of, for a linear chain CO2 kind of molecules. Another one is triangular molecules, NH3 type molecule. Okay, molecule. So there are 3 L. Here L is equal to 2. So you have got 3 into 3, 9 minus 2 is equal to 7, and 9 minus 3 is equal to 6. So CV can be, U can be written as, actually both U will be there. So 7 by 2, suppose this is R into T. Also it can be 3RT also, 3RT, because 6 by 2 RT, so 3RT also. Okay, so what will be the CV? CV can be again 2, 7 by R, 7 by 2 R, or it can be 3R. And CP will be CP will be CP plus R. So one will be 9 by 2 R, and another can be CP plus, so 4. Okay, CP CV plus R, that means 4R. Okay, now you can take ratio of these two. Ratio of that will be, gamma will be 9 by 7. Okay, so 9 by 7 means, so there will be 2. So 1.28 nearly, 1.28 gamma, and another point is actually the CP. So 4 by 3, 4 by 3 is almost 1.33, 4 by 3. So 1.33. There are two possibilities of gamma also. Okay, so this is how you can calculate specific heat, then the ratio of Cp by Cv from this particular uh, session, whatever we have discussed, degrees of freedom, laws of equipartition of energy, and specific heat capacity. So we'll stop it here for today, and next day I'll message when we can meet. We'll in the next class we'll complete this kinetic theory of gas, and Monday onwards we'll start a new chapter again. Okay, so bye for today.